what happens when we change the mass of these particles? Okay, well, for a same incident energy, so if let's say my heavy particle and light particle had the same kinetic energy, right, then the heavy particle will experience more dampening than the light particle. So in other words, it'll have a smaller transmission probability for the same given kinetic energy, which is kind of to be expected. And so now to demonstrate that, this is what you're going to do in your Mathematica assignment. And I'm just going to demonstrate this through the two graphs that I have. And we'll get into this more in our Friday discussion. But here what I have, these are realistic calculations using electron mass. So this first graph. So I actually used the electron mass, and I made the barrier 10 electron volts. And what I have here on this X scale is the length of the barrier, okay? And you can also see now these are looking at different incident energy levels. So for example, 10 electron volts is the potential energy barrier for this tunneling problem that we did here, that I did here. And then so when E over V is 0.5, that means the kinetic energy of the electron is 5 electron volts, right? So when it's 0.7, it's 7 electron volts. When that number is 0.9, it's 9 electron volts. And as you can see, right, the higher that incident energy is, the longer of a distance the electron can tunnel, right? So like if I look at the, let's say 3 angstrom, and again, these are realistic calculations, real numbers that I put in here, okay? 10 electron volts barrier, and let's say 3 angstrom, you can see only the particle with 9 electron volts has any decent chance of tunneling through, right? And so as you can see, as the kinetic energy gets smaller, that tunneling distance, you know, where it can actually make it through really falls off. But all the same, we notice that this is a pretty big scale that electrons are able to tunnel over, you know, between, you know, 1 and nearly 4 or 5 angstrom. That's a really big distance. But check out what happens when I change this to a proton. So now this is proton tunneling probability, okay? Same barrier energies, 10 electron volt potential energy, but now look, even the most energetic proton here, the one with 9 electron volt kinetic energy, can't even make it a quarter of an angstrom, right? It makes it, you know, maybe 1/10, maybe 0.15 of an angstrom, but that's it. So oftentimes in experimentation, when you want to prove that tunneling is a valid mechanism, what people will often do is compare the experimental result with a proton versus that with deuterium. Because even the proton falls off at a really, really short distance, okay? If I were to replace this proton with deuterium, right, then there's no way the tunneling will happen at all. And so that's a really good indication that people use experimentally to prove tunneling is a valid mechanism, specifically in kinetics. When they see something is happening so fast, the only way it could happen is if, you know, a proton tunnels right through a barrier in the case of a proton transfer reaction. You replace that with a deuterated sample, and if the reaction cuts off, then very likely tunneling was involved in the reaction, okay? So heavy particles, you know, typically a proton, and light particles, typically an electron, or you could even compare protons and deuteriums, or even protons, deuteriums, and alpha particles, right? You can compare all these different masses, okay? So now what we have over here is now going back to the particle in the box problem. Hopefully this looks familiar to you, okay? And what I want you to recall, when we originally did the particle in the box problem, when we said this is an infinite square well, our wave functions looked a little bit differently. They actually looked like this, okay, with no tunneling whatsoever into those barriers, because we put the particle in what we call an infinite square well. Well, as it turns out, because of this tunneling, And because we're never going to have infinitely large potential energy boxes, right? Then realistically, in this particle in a box problem, or particle in a sphere, particle in a cube, we do see a little bit of tunneling on the borders of these boxes. So some small amount of tunneling is possible into the box barrier, okay? And then similarly, if we go up to the n is equal to 2 level, we still see features that we saw similarly to the particle in a box. However, right, more tunneling into that barrier. And what I also want to indicate, okay, so I'm just going to write this equation down directly. If from this we can also predict how many what I will call bound states are in this potential energy box. And by bound states, we mean states that are in that box that very likely can't get out. We will later call these bound states orbitals. Okay? So there's an equation that comes as n minus 1 is less than 8 mvl over h bar squared square root is less than n, where n is the number of states. And what's important to note about this relation here, what this predicts is, you can see now the number of bound states, that's n, okay? It will increase as the length of the box gets wider, and it will also increase as the depth of the well gets bigger. So in other words, as the potential energy increases, and now we're kind of moving past this tunneling thing and combining this idea of tunneling and the particle in the box, okay? If the potential energy increases, which we can think of as the well is getting deeper, okay, we get more states. If the length of the box gets wider, we also predict to get more states. And that's actually a direct result from statistical mechanics. So